Hello, everyone. This is Matt Legler over at Cybergenetics. I'd like to welcome everyone to our TrueAllele user group session today. I'd like to thank everyone for attending. Today, we will have Dr. Susan Greenspoon uh, discussing her experience with TrueAllele casework, both in validation and in admissibility. And as she gives this presentation, you're free to submit questions using the GoToWebinar control panel. And then we'll try to answer as many questions as time permits after the presentation. So without further ado, I will turn it over to Dr. Greenspoon. And Susan, I am giving you control of the computer now.
Okay. All right. Good afternoon, everybody. I'll be talking today about our work in validating TrueAllele casework, but also we really wanted to get a good idea of what the limits are for this software program, because we'd heard quite a bit about it, and we wanted to push the boundaries as much as possible. All right, let's see. Okay, so oops. As everybody is aware of, TrueAllele casework is a continuous probabilistic modeling statistical software for both evidence and reference profile analysis. It utilizes the Markov chain Monte Carlo sampling of the data, which searches and samples the data for a best explanation. And this, in this figure on this slide, you can just see a three-person mixture, and the different colors indicate the allele proportion from each contributor. So once we perform a TrueAllele analysis, TrueAllele casework analysis for a particular profile, electrophoregram data, we go through a series of steps where we assess the overall analysis itself. So we assess the MCMC chain, and we kind of classified it as ideal or non-ideal. And I'll talk more about that later, but only the ideal analyses were used to later assess genotype concordance. And you've probably heard from presentations by Dr. Perlin that one of the requirements for reporting your results from a TrueAllele casework analysis is that you've got reproducibility. Now, I'll give you an example of what we assessed as an ideal Markov chain Monte Carlo analysis or sampling for a three-person mixture. So what you see on the slide here on the top panel is the histogram distribution around the mean for mixture weights. And you can see there's a broad distribution around that mean. And I would expect that because it's a complex three-person mixture. Down below, the lower panel is the Mcmc sampling. It's a history of the Mcmc sampling, this Markov chain. And again, there's a great deal of sampling, and as I said, I would expect that given the complexity of this mixture. So this is termed ideal. Now, for this same three-person complex mixture, what I'm showing you on the right-hand side is what we classified as not ideal, non-ideal. And the top panel shows slim distributions around the mean for the mixture weights. And then the bottom panel is the history of the Markov chain sampling. And again, it's in our experiences and opinion, it winds up being non-ideal given the complexity of that mixture. And I'll talk a little bit more about that in a minute. But we also assess other metrics, the convergence, which is this Gelman-Rubin statistic, the consistent mixture weights between independent analyses, because you expect and we want to see reproducibility, and then the match statistic concordance, which is given in log likelihood ratio values. And we expect those to be within 2 log units for reproducible runs. Okay, so as I said, when we have 2 ideal analyses, we then would assess these for genotype concordance. This is for the derived contributors after TrueAllele has analyzed these samples and derived the contributors. Now on this top panel is that same 3-person mixture, and it's difficult to follow this completely, but this is the THO1 locus, and what you're seeing is a distribution, because it is a 3-person mixture, so there's some uncertainty, genotype uncertainty. But what I want you to take home from this on this top panel is what I'm comparing are 2 ideal analyses, and you can see these bars really line up. So the 3 derived contributors from one independent analysis are the 3 dark blue bars. The 3 derived contributors from another independent ideal analyses are the light blue bars. In fact, when we why is that not showing up? Here we go. When we compare the derived contributors to the actual contributors to this mixture, since I made the mixture myself, you can see that the derived contributors, that there's a high, the major contributor has a 100% probability of this 7.9.3 genotype, and then there are lower probabilities, but still probabilities associated with the other genotypes of the true contributors. On the bottom panel, what I've got is that same ideal analysis of this 3-person mixture, but it's compared with a non-ideal analysis. And so the 3 light blue bars is the same ideal analysis as in the top panel. But the non-ideal analysis, which I showed you in the previous slide, is indicated by the 3 dark blue bars. So those are the 3 derived contributors, and it assigned 100% probability in that non-ideal analysis. Now, as you can see, 2 of the derived contributors for the non-ideal analysis are certainly correct, but this last one, the 715, is not. And so there was not good genotype concordance between the ideal and the non-ideal analysis. All right, so for the validation study, what we did is utilize mock casework samples, which included 17 single source profiles, and we didn't want to test just straightforward high quality single source profiles. We wanted to simulate more of what we might see as challenging casework single source samples. So these were degraded and stochastic samples. We assessed 18 2-person mixtures, 14 3-person mixtures, and 7 4-person mixture profiles. There's a little bit of a delay here in slide changes. We also, so what we wanted to test then when we performed our validation work with the TrueAllele casework is how TrueAllele casework handled these single source samples with a lot of allelic and locus dropout. We wanted to evaluate the reproducibility of the process, the accuracy of the TrueAllele process. And by accuracy, I mean exclusion of non-contributors, inclusion of true contributors, the mixture weight assessment of 2-person mixtures. I limited the mixture weight assessment to just 2-person mixtures since I could do that manually and compare, whereas beyond a 2-person mixture it becomes difficult to do that. We assessed the sensitivity of the TrueAllele process, and by that what I mean is the minor contribution level below which provided a negative log likelihood ratio. In other words, below that level, there was just insufficient support for this individual to be a contributor to the mixture. We evaluated the specificity of the TrueAllele process. And for that, I mean the elimination of non-contributors as well as the elimination of relatives to true contributors of the mixture. So let's move on to results. In this slide, I'm showing you our results with a few degraded DNA samples. Those are indicated on the y-axis, and each of those sample types, the 80 degrees centigrade, UV treated, 56 degrees centigrade, and 37 degrees centigrade, each of those samples were incubated for a period of 3 months. So there were different levels of degradation observed in these samples. Now, what is being plotted then in blue is the log likelihood ratio. In green is the sister allele not observed, and in red is the number of alleles observed in that single source sample, both above and below the limit of detection or our analytical threshold. And what I'd like you to notice is that the log likelihood ratio in blue tracks pretty well with the number of alleles observed for that sample, as you would expect. But there is one exclusion to that, and that is the UV treated sample. But the UV treated sample had a large number of genotypes where the sister allele was not observed. In other words, it was a false homozygote. So what happened is that false homozygote caused there to be a high probability assessed for a homozygote at that locus, as you would expect, since the sister allele was not observed at all, and a low probability for the heterozygote genotype, and therefore that resulted in this case, a negative log likelihood ratio when that sample was compared back to the reference profile. Now, this phenomenon was observed again with the stochastic samples. And here I have 10 stochastic samples. The top 5 are PF, 2 at 30 picograms of input genomic template, and 3 at 10 picograms of input genomic template on the y-axis, and BC, another sample, 3 at 30 picograms of input template, and 2 at 10 picograms of input template. PF is indicated in red, BC in blue, and what we have on the x-axis is the log likelihood ratio. So when PF is compared with BC, as you would expect, BC is in blue, all those log likelihood ratios were negative because that's not its reference profile. When it was compared with PF, you see positive log likelihood ratios that are pretty large, except for one sample at 10 picograms. There were another 2 samples at 10 picograms that did give positive log likelihood ratios, but one provided a negative log likelihood ratio. And again, for the BC samples down below, the bottom 5, you can see when the BC samples were compared with PF, all of them generated very large negative log likelihood ratios, as you'd expect, whereas 2 of the BC samples, the 10 picogram samples, also generated negative log likelihood ratios when compared back to its own reference profile. And again, it was the same phenomenon, a preponderance of false homozygotes that drove that log likelihood ratio low or into negative territory. All right, so I want to move on now to the results with the mixture samples. Now, for all of the mixtures, and this is a very busy table, but I will blow up an example and walk you through it in just a moment. But all of the 2, 3, and 4 person mixtures tested were tested against a panel of 11 reference profiles. And the true contributors to the 2, 3, and 4 person mixtures were among the 11 reference profiles. All right, so let's take a look at one of these that winds up being interesting. And at first, let me explain across the top what all these columns represent. On the left-hand side, we've got the sample, the MC quality, as I told you about earlier. We assessed it as ideal or non-ideal, and only the ideal samples were used for genotype concordance. We assess the convergence value, which ideally we want it to be 1.2 or lower, although you can utilize convergence value, samples with convergence values higher than that. The mixture weights we wanted to assess between runs because they should be reasonably consistent. The log likelihood ratios, also we want those to be within 2 log units for reproducibility. And then we assess whether the non-contributors were excluded and the genotype concordance. So this sample, mix 1, is supposed to be a mixture of sample S11 and S9, with S11 being just a 3% contributor to this mixture. And I analyzed the sample at 25,000 and 100,000. That's what the K refers to, cycles for the TrueAllele process. And what I'd like you to notice here is when we look at the log likelihood ratio, you can see I have it indicated in terms of a hierarchy. The most major contributors listed first, and then as the contribution level reduces, then they're listed after that. So you can see between these 2 runs for sample S9, the major contributor, they have very consistent log likelihood ratios, very large numbers. But for S11, we have negative values. They're not even very consistent with each other. So let's take a look at the sample to assess why we're getting such large negative log likelihood ratios for that minor contributor. So this is mixture 1, and at first glance, what it looks like is a single source profile with kind of a noisy baseline. But if you look at D3 and FO1, this is PowerPlex 16. If you look at D3 and FO1, what you can see is there are actually 2 very small peaks among a lot of noise at the baseline, and those are the only peaks that correspond with that minor contributor. So TrueAllele came back with the answer that there was really insufficient support for that minor contributor being a contributor to this sample, and I would agree with that. Okay, so let's move on to mixture weight assessment. In this graph, what I'm showing you are the 2-person mixtures, and those are listed across the bottom on the x-axis, and on the y-axis then I have the mixture weight for the minor contributor. In green is the mixture weight estimated based on the quantitation of the DNA samples. In red is my manual calculation for the mixture weight based on, I use the breakout loci to estimate the mixture weight for the minor contributor. And then in blue is the TrueAllele derived mixture weight. And what you can see if you look at the right side of this graph is that the mixture weight based on the quant estimate in green and the manual calculation in red and the TrueAllele derived all track pretty well with each other. They're all quite consistent. But if you look on the left-hand side, you'll see that mix 2 through 7, while the manual and the TrueAllele derived values are consistent with each other, the green is not very consistent. And I'll tell you right now that the concentration for one of the samples was off. But let's take a look at mix 5, which winds up being kind of interesting because I don't have a manual calculation for that sample, and you'll see why in just a moment. But based on the DNA concentration estimates, the minor contributor should constitute 20% of that mixture. Based on TrueAllele derived mixture weights, the minor contributor, well, there is no minor contributor because it's really a 50-50 mixture. So let's look at the sample. And here's mixture 5, and you can see there are quite a few breakout loci, and in fact, it looks very close to a 50-50 mixture. So TrueAllele got it right. I'm going to move on to 3-person mixtures, and again, it's a busy table, and I'm just going to zoom in on one sample that winds up being pretty interesting. I do want to let you know that in yellow are, I have labeled in yellow the analyses that were non-ideal, and so they were not utilized for genotype concordance. That's all that means. But let's take a look at one sample, mixture 4. You can see right away there's a lot of yellow. And in fact, you're looking at 7 independent analyses of mixture 4, and only one of them was I totally satisfied with, that it was an ideal analysis. And I thought, this is odd. This is a 3-person mixture, and why am I having such a difficult time generating perfect ideal analyses? So I went back to that sample and took a look at it, that electrophoregram in G. What jumps out at me is, wow, I've got a really gigantic polymer spike in that sample. Duh. And so I went back into TrueAllele, and I edited out all the allele information associated with that polymer spike and reanalyzed the sample. And so when I did that, lo and behold, the bottom 3 rows are mixture 4 edited. You can see that I generated 2 additional ideal analyses, and even the one in yellow was pretty good. But you can see, if you look at the log likelihood ratios, that's what I have circled, that the log likelihood ratios for the 3 contributors are very consistent and close to each other, as you would want for reproducible analyses. And when you compare it to my original analysis that included that polymer spike, you can see that the 2 new ideal analyses generated higher match statistics for all 3 contributors. And the reason for that is by editing out that polymer spike, I reduced the genotype uncertainty and increased genotype certainty for the subsequent TrueAllele analyses of that same data. So that brings me to the question of reproducibility. How reproducible is this process? Because I told you we were going to assess that. Well, let's take a look at these 3-person mixtures. And what you're looking at is the log likelihood ratio plotted on the y-axis, and it's the average value. The n frequently is only 2, but for some of these it's higher. But these are the derived contributors for these 3-person mixture samples, and the replicate analyses, and just how reproducible are those log likelihood ratios. And what you can see is that the standard deviations are really very small. These runs really are quite reproducible. And this is that mixture 4 edited, which showed a little bit more variation, but still quite reproducible. The same is true for the 4-person mixtures, which again is very complex. I'm not showing you the 2-person because those are almost identical from run to run. For the 4-person mixtures, again, the n ranges from 2 to 4, and again, you can see that the standard deviations are pretty darn small. So let's move on. Here's a chart summarizing the 4-person mixture data. And again, I'm going to zoom in on an interesting sample, and that is mixture number 17. This mixture, I analyzed 8 independent analyses, and I've got 4 that I consider to be ideal. And what you can see, if you look in the column, you don't see the heading, but the column says 7 tested, and those were the non-contributors that it was compared against. And you can see that in most cases, in 2 of the ideal analyses, all non-contributors were excluded or gave negative log likelihood ratios. But in another 2, and they're indicated in red for that non-contributor, a very small log likelihood ratio was generated for a non-contributor to this 4-person mixture. So let's take a look at that electrophoregram data to get an explanation for why that might be the case. Okay, this is mixture 17. It's 4-person mixture. What I'm showing you now with the pink ovals is everywhere you see a pink oval, that non-contributor S4 shares an allele with this mixture. And you can see there's an enormous amount of allele sharing at every single locus. Now, what you can also see is I have 3 examples here at VWA, TPOX, and D16. I've got a peak that is in a stutter position that's consistent with that non-contributor to the mixture. So if I were doing this manually, I would have a really hard time excluding that individual as a contributor to this mixture. The TrueAllele generated inconclusive results because we generated 2 runs where this individual provided a negative log likelihood ratio and 2 where there was a very small positive log likelihood ratio. All right, so now that's a good segue into specificity. The specificity is the ability of the TrueAllele analysis process to provide a negative log the specificity, the ability to exclude or provide a negative log likelihood ratio for non-contributors to a mixture. So what I did is I utilized the derived contributors from the TrueAllele analyses, only the ideal were used for this, for the 2, 3, and 4-person mixture samples. And I compared those derived contributors against 100 synthetic reference profiles. And what I have plotted here is the largest log likelihood ratio generated from those comparisons. And so that means if it's a negative, it's the least negative value. And you can see for the 2-person mixtures, all of them generated negative log likelihood ratios. For the 3-person mixtures, all of them generated negative log likelihood ratio values. And for the 4-person mixtures, they're less negative, as you can see, but all but 1 actually generated negative log likelihood ratio values. And it's a very small positive match score to this synthetic reference profile. And it was not reproducible. It wound up being 2.9 times more likely than a coincidental match. And this is out of a total of 21,400 comparisons. So there was 1 false match out of 21,400 comparisons. And waiting for the next slide. Here we go. So we also assessed the specificity for of the TrueAllele process, the ability of the TrueAllele process to exclude or provide negative log likelihood ratios for first-degree relatives to the 2 contributors of a mixture. And so what I did is I created 7 sons and 5 brothers from the references used in the study, and I compared those to the 2, 3, and 4-person deconvoluted mixtures, analyzed mixtures of the TrueAllele process. And what I'm showing you is a table of the results only for the sons, because for the brothers, only 1 3-person mixture provided a positive log likelihood ratio, and that was not reproducible. What you're seeing are only the examples in this table where the son actually did generate a positive match score. So what I have are 3 3-person mixtures. There's mixture 1 and mixture 2. Both of these are 2 separate analyses of these 2 mixture profiles. And both mixture 1 and mixture 2 generated small positive reproducible match scores for the son of BC. BC is indicated in yellow, and he is a true contributor, as well as KMH and NH to these 3-person mixtures. Mixture 4 edited also provided a small positive match score to the son of NH, which is a true contributor to the mixture. That was not reproducible. For mixture 19, what we see is 4 different independent analyses of mixture 19. 2 of those provide the son of NH, who is a true contributor, did not provide a positive match score. And 2, the son of NH did provide a positive log likelihood ratio, but it was not reproducible. We're getting mixed results here. It's interesting to note that NH was the most minor contributor to mixture 19 and displayed a lot of allelic and locus dropout and provided a negative log likelihood ratio. And he's a true contributor. But the son just so happened to share a couple more alleles with the mixture, and so it drove it non-reproducibly, but it drove it into generating positive match scores in 2 instances. Okay, so in summary, we analyzed 17 stochastic and degraded single source profiles, and negative match scores may be generated when compared back to the reference profile if that sample has many false homozygotes. We analyzed 39 mixture profiles. There were 18 2-person, 14 3-person, and 7 4-person. All the non-contributors were excluded except for 1 4-person mixture, and that was number 17, where a non-reproducible log likelihood ratio was generated for a non-contributor. It's possible if we had run this additional times or for longer cycles that we could have conclusively resolved this, but for the purposes of this study, it was just inconclusive. Assumed knowns can increase the match statistic by reducing genotype uncertainty, but I didn't, we did do that analysis as part of our validation study. I just didn't present it here. First degree relatives to 2-person mixtures were all excluded, but positive small positive match scores were generated for 3 and 4-person mixtures for actually 5 samples for the first degree relatives. And only 2 of those, only to 2 mixtures were those results reproducible. The other 3 were not. And for the specificity test, we compared 214 derived contributors from the 2, 3, and 4-person mixtures to 100 random reference profiles for a total of 21,400 comparisons, and there was only 1 false positive, and that was to a 4-person mixture, which was only 2.9 times more likely than a coincidental match. So in conclusion, TrueAllele casework is accurate. Non-contributors were excluded except for 1 example of inconclusive, and contributors were included. We did have 3 examples where the most minor contributor provided a negative log likelihood ratio, and those were instances of where there was a great deal of allelic and locus dropout. TrueAllele casework is highly specific. We only had 1 false positive out of 21,400 comparisons for the 2, 3, and 4-person mixtures. And it is sensitive. We did find that when the minor contributor is 10% or below, a negative log likelihood ratio may be generated, but not always. And it also may produce a small positive match score for a first-degree relative to a 3 and 4-person mixture. And then if you use a correct assumed known, then a higher match score may result. So now I want to briefly go over our admissibility hearing and sort of relay to you how that went. So TrueAllele was used for mixture analysis in a capital murder case, and this was outsourced to cybergenetics because we were not online with in-house use of TrueAllele casework yet. Dr. Mark Perlin was subpoenaed to testify, and a number of Virginia Department of Forensic Science staff were also subpoenaed. Kathy Shannon was subpoenaed to testify about her DNA work. Lisa Shearmeyer Wood, a supervisor, was subpoenaed to testify on the SWIG-DAM guidelines, which pertain to probabilistic modeling and selection of cybergenetics for outsourcing. Brad Jenkins was subpoenaed to testify about the financial commitment that EFS made to cybergenetics. And then I was subpoenaed to testify about our validation data, since it was an independent assessment of the TrueAllele Casework product. Now, this hearing lasted for an entire week. Dr. Perlin testified for 2.5 days, and it was pretty grueling, but he held his own ground. Kathy, Lisa, and Brad each testified for 1 to 2 hours. I testified for about 5 hours, and there were 3 defense expert witnesses, and only one of them testified for half a day. The main criticisms were that cybergenetics does not make the source code available for the software. They also criticized the use of MCMC for statistical sampling, but that was really quashed by many, many examples provided by Dr. Perlin of its use, of its widespread use. They attacked the validation data for having many unused runs. For the 2 4-person mixtures where the most minor contributor produced a negative log likelihood ratio. They criticized that some of the 3- and 4-person mixtures displayed positive log likelihood ratios for the first-degree relatives of the true contributors to the mixture, and there were a few other complaints. The judge ultimately ruled TrueAllele admissible, and in his ruling he stated that TrueAllele Casework was a valuable tool. So I'd like to acknowledge cybergenetics. It's not coming up too rapidly, but Mark Perlin at cybergenetics, Matt Legler, and Bill Allen, and then at DFS, our program manager Brad Jenkins, and then our TrueAllele team, which is 4 people. It's not coming up here, but here we go. Lisa Sherman-Wood, Kathy Shannon's not on the team, but she did the DNA. Angie Rainey and Lee Collins are also part of our TrueAllele team. So I can take any questions you may have.